Okay, let's now have a look on the predictive controllers. This is a class of controllers which are very successful, used in also in chemical industry, and the idea is of course also more than 20 years old. But I have seen this idea in presentation day-to-day presentation at the Fachhochschule Köln. There was the father of the idea of the PFC, the predictive functional control. It's one type of a predictive controller, and he presents this with industrial experience. It was impressive, but not so easy to understand. The idea, the basic idea, was very interesting. The complete predictive functional control of Mr. Richalet is described in this paper. Maybe you, if you are interested to step more deeper into the details, just take the book of Mr. Richalet. A short German paper is then published from Professor Haber, that was a leader of the control system section in the FH Köln. I can give you a copy of this paper. The idea is very simple and impressive. It comes from the fact that computers, this is done with a digital computer, are more and more powerful in the last years, and they can do much more calculation work in much less time. So we have powerful microcomputers, and the idea is use this power in each step, in each sampling time, in each sampling period, to optimize the controller behavior by using, and now the basic ideas, by using a model of the process. You need a good model. That is the industrial process, the analog one, still the position control, temperature control, what else? This is the physical output measured by a sensor. Try to find a very good fitting model in f of z. Yeah, so this should be a step response invariant system, or identified with one of the methods I described in chapter 8. Independent of this, we assume that we have a model, and now to compare this with PID or deadbeat controller design we have learned in previous steps. The process model is in PID and deadbeat controllers used to design the Q's and P's, and then the model is not ever used. Then we throw away the model. Therefore, we use, before we start running the controller in the loop, we use the model, design the controller parameters, and then these controller parameters are fixed, are unchanged, and the model is never used again. In difference to the predictive controllers, the model is used in each step. If you sample with 1 millisecond, 1,000 times a second. And the idea is, okay, I want to have an optimal controller output for this process. First, before I send this to the process, I send this y or any proposal for a good y to my model and check what will the model do with your controller output, or in other words, how can I find methods, algorithms to optimize the y to get a very good model output fitting to our desired value. Yeah. So first I play with my model in different ways. This gives different types of controllers. For example, to look into the future. With a model, I can calculate with a given y, xm plus 1, xm plus 2, I can predict the future of the process output with my model. That is the reason why these controller types called predictive controllers. we look into the future. In my first version I want to present, we look into the future depending on the degree of the process, 5 to 7 steps. In the Rijalet version of predictive functional control, we can decide how many steps we want to see into the future. Yeah, so we can use this model and calculate 1,000 steps into the future with our controller or controller output. If we have found a good y to get good xm's, then I send y to the real process, wait the next step, get feedback to my controller algorithm what is a real x value, get back with the given y what is the model xm value, put all this knowledge together to calculate the next y value to get optimal output. So in each step we try to optimize the y value using the model. I will show you this idea in a very simple example. Yeah, this is an idea. I like this idea. The predictive controller is comes in one of the next chapter. First, I show you this idea leads myself to develop a special version of the deadbeat controller. You will see what happens. This idea, together with the original deadbeat controller knowledge, gives a new type of controller which you will understand, because it is easy to understand, because the manual work through this is simple. So let's assume a PT1 process, and I assume that I have a model. I have the K and the T, so the A1 and the B1 of my model, which are identified, or I know them, or what else. Yeah, so I know the A1 and the B1 of my PT1 model, and this should fit to my real process. Then you see here the equations is the following. That is the transfer function of my model. This is a model output, and this is my controller output. The controller influences the input of my model, and this can then calculate xn. So that is the step. Let's do this in manual work on the paper. Yeah, 9.7 predictive controller with PT1 example. The PT1 example leads to a model which is the step response invariant type of model. So we have model output, which is just a copy of the equation of my paper. You will see y of z is the controller output, and this gives a b1 z to the power of -1 divided by 1 plus a1 z to the power of -1. Model degree is 1, is clear, and we can now convert this into my algorithm. The output, model output at position k, or what else you need for a letter, can then be calculated. This is b1 times y of k minus 1. b1 is a numerator time constant. 1 z to the power of 1 minus 1 means 1 delay. It's -1 multiplied with the input of my model. My model is, I should indicate this with an M. This is H0 f m of z. Y is the input, and X model is the output. So V1 minus, not plus, minus A1 times input signal, output signal is the recursive term, xmk minus 1. Okay, this is very simple, nothing new. That's the original conversion of my controller. If I have an f of p, pt1 with k divided by 1 plus pt, then in the paper you can find that the a1 is negative e to the power of minus sampling time divided by time constant, and b1 is nothing else than k times 1 plus a1. In our example, I want to use the following values. K is 0.4, T1 is, T is 1 second, and sampling time is 100 millisecond, 0.1 second. This leads to values of A's and B's. Now then I can calculate A1. A1 is a negative 0.9048. 4 significant digits are enough, and that is 0.03807. Yeah, so this example with these numbers gives A's and B's. So with this A's and B's, I can calculate model output depending on controller output one step in the past. Now the idea is the following. Now I calculate the model output one step in the future. One step in the future means with my model I can look into the future. I can now calculate xm of k plus 1, xm of k plus 2 and so on, depending on controller output. So I can look with my model into the future. That means here I have y of k minus a1 xm of k. Okay, so what can I work with this equation? This equation has the actual controller output, and that is really that what I want to have. Solve to it. Yeah, I want to have y of k. Then this is the actual process output. I can now replace the model xm of k to the actual measure. This is known, yeah, that's the actual process output. And what is this? This is my goal. That is the the controller output one step into the future. And of course, I want to be fast. I can say, okay, desired value, set to y, set to w. Yeah, set this to desired value. If you don't want to be so fast, then of course you can say, okay, give me half of the value, or 1/3 or 1/4 of the desired value. But I want to show you what happens if I say, okay, in one step I want to have the desired value, and then I have the deadbeat controller. So with this I am exactly as fast as a deadbeat controller if I can solve this equation. And I think you see this could not be so difficult now to calculate this equation with the given values. That is my desired value, which is known. That is the B1 coming from the process. That is my desired and my actual controller output I want to calculate. And this is the actual process output. So I solve to y of k. This gives y of k is, in the numerator I have w, desired value, minus a1 times x of k. Actual value of x divided by b1. That's all. Yeah? Is the calculated output of controller. Yeah, and then if I have this, calculate this, you see the control difference is not anymore used. Here, this control algorithm needs the value of w, needs the process value. This is not the control difference. W minus x was the control difference. That is different to this. Yeah, so this is a difference to previous controllers. The predictive controllers need information not only of the control difference, but on the desired value and on the control value. Okay, let's make just an example. Say what happens with reference step response. Now we can, because this is simple numbers, we can calculate the values step by step, which we reach if we want to have reference step response. W should be 1. We assume that we have 0 initial conditions. It's clear. All signals, if we start, should be 0. And here we calculate the y of k. Oh, this is k, sorry. This is k, y of k. And let's start with k0. Y of 0 is, now I want to have the 1 here, minus a1. a1 is, sorry, minus a1? No, I have to bring, sorry, minus error. This has a negative sign. This has to be put to the other side. Sorry, I have a plus sign here. Doesn't matter. I found the error, so I have corrected this. W is 1 plus A1. A1 is negative. Now negative 0.9048 divided by 0.03807. What is this for a value? This calculated gives a value of 26.27. Okay, the 26.27 value is sent to the controller, but now we have a limitation. We know this. Y of L is limited. Now I know, okay, I have only 10 volt. More as 10 volt is not available. So I send to the controller 10 volt. So what is the process now doing? The process can be calculated x of 1. Here we need a last column. Sorry for this. Yeah. x1, x is 0 here, of course, 0 initial condition. The x1 now can be calculated with my process model equation. If we assume that the process behaves like my model, then x1 is b1 times, now this is y of 0, and this was 10 volt, 10 minus any value times 0, because the value xm of 0 was 0. So we know this is B1 times 10. B1 is 0.038. So this is 0.3807. So we know 0.3807 is the value we reach after one step. Doesn't matter. Now we continue with my calculation. I measure my actual control output. I measure my actual process output for the next step. And I can calculate y of 1. Y of 1. Now this equation calculates my new controller value. Y of 1 is 1. Desired value is still 1. Plus A1, 0.9048 times. And this is now the actual process output. I can use a model value, but also I should use the measured value. Then of course we have in our calculation the possibility here to not to calculate with the model output value, but with the correct measured sensor output value. Then we have a real feedback divided by 0.03807. If you put this into your calculator, you get the value of 17.22. So the controller want to reach the desired value in one step, want to have 17 volt. Gets only 10 volt. So I can calculate now the x2 value. This value with my model is 1 minus 0.9048 times warte mal, x, Quatsch, wo ist x? X, hier. Das ist Käsekram. Falsch. Again. x2 has to be calculated. x2 is B1 0.03807 times 10 volt. More than 10 volt you cannot get out of my actuator. Minus A1, so plus 0.9048 times the x value one step before. This was 0.3807. If we calculate this value, we get 0.725. So the process output goes to 0.725. And now we get the last step. You will see what happens in the last step. Now I can calculate with my model, with my prediction here. With my prediction, I calculate y of 2 is 1 minus 0.9048 times 0.725 divided by 0.03807, and this value is then 9.035. The controller want to have 9.035, and of course this is less than my limitation, so the controller gets this value 9.035, and you will see what happens after one further step. The x3 value is how large? Is 0.03807 times 9.035 plus 0.9048 times the last value is 0.725. And this, if you put all numbers into your calculator, should be 1. So with the last step we reach automatically 1, and now y of 3 is calculated to 1 is a desired value, minus A1 is negative negative 0.9048 times 1, which is reached, divided by B1, 0.03807, and this value is 2.5. 2.5, which means the controller output goes to 2.5, gets its 2.5, and if you look back to my process K, you see the K is 0.4. Now the 2.5 is exactly that value which holds the output at 1. And now this is unchanged for the next steps, so the controller stays exactly at that value which is necessary to hold the output at my desired value 1. So you see, this controller includes the limitation. It calculates the step to get the desired value, and if this takes longer because of limitation, it doesn't matter. The last step is exactly calculated in that way that I am coming from the last step exactly with the 9 volt value to the final value 1. So this is as fast as a deadbeat controller if you have no limitation, but is much faster without any overshoot if there is a limitation. So this is just a better deadbeat controller. I have not found, really have not looked into, I haven't looked into the literature of the name of this, because I have developed it here in my lecture. I call this deadbeat Y. So deadbeat Y with degree 1 is working very well, and in the next video I will show you how to come to this controller and to play with this controller and compare this controller with our previous types of controllers. Okay.